All right, CNT125, we are on Chapter 9. We're continuing our different WAN connection options. They introduce us to MPLS, multi-protocol label switching. This is a type of technology that allows multiple different layer 3 protocols to travel over connection layer 2 protocols. And now you have routers that are acting more like switches. This actually moves data through relatively quickly, and this is showing you here the ISP might have MPLS to move connections between different sites quickly. So how it's doing that, this came out late 90s, early 2000s, can handle many different types of payloads, often used by the ISP to move data through quickly. And what happens is your data that's moving through has an extra little header slid in there, and it's read by your routers quicker than reading the IP header, so it's trying to move the data through a little bit quicker. Highly scalable. Customers can prioritize their traffic. The ability to label traffic offers more reliability and even quicker service in some cases too. So here again, that picture, but you can do some quality of service with this and even have a little bit more efficient routes. And the reason and how it's doing that is right here. If I would have my normal Ethernet header, layer 2, layer 3 header, this MPLS label called a shim gets slid in here. And the routers can read this quicker than your IP header and move data through a little bit quicker. So they call this as layer 2.5, if you will. And it allows moving the data through a little bit quicker than just handling IP packets as it's moving through. So it can actually move data through from customer to customer, whether it be at the ISP or almost a pathway from customer to customer. So you might run into some MPLS. So again, familiarity is the key on some of these technologies that they talk about. Different cloud connectivity options. Okay. We need to have a reliable connection to our cloud provider resources. Think about when we were doing our Amazon Web Services lab, we were just using our regular internet connection. That is okay for, kind of low-level connection or low-level need. As we have more resources, we might need a more dedicated connection or even a more direct connection, if you will, so that I can have my data move there completely and thoroughly all the time instead of just being routed through the internet too. Might even set up a VPN to go directly from our site to the cloud services, cloud resources that we have. This brings us up the term of a colocation, colo, that might get used. A colocation, we have a whole bunch of your cloud service providers into this colocation facility, and we could connect into there. So I would have, if I have a direct connection to there, I would then have a connection to any and all cloud resources that I might be using or subscribing to. I pulled up a map of PA showing different cloud connection options. These are different data centers around PA. You notice there's a large percentage out Pittsburgh, large percentage in Philadelphia, major cities. These are all potential colocation facilities that you could be connecting to. So, if I have a business here in Harrisburg, I might connect to Harrisburg one, but I might even look at connecting to Philly or Pittsburgh. They're still close enough that if I had issues, I could drive to those cities and look at equipment or deal with equipment if necessary. I pulled up one or two of those companies that were on that map, showing you that they're colocation services. And here's even one, Iron Mountain and so forth. So different companies providing that connection service. Software-defined WAN, software-defined network, software-defined WAN. Again, we now have a controller telling the individual devices what to do. So instead of us programming every individual device, we tell the controller at the upper level, hey, I want this thing to occur, and it communicates with the devices to make that happen. So some benefits we get out of are these right here, and I have these broken out in the next couple slides for you. They say transport agnostic because it can go across many different types of WAN connections, wireless, broadband, here's MPLS, etc. and showing again many different connection options here. My controller is the one that says, hey, make this happen, whatever you need to use to do that, etc. Whatever's available to use, do that. Also, application-aware routing and active load balancing for failover. Again, the controller can direct traffic through any connections that we have and try to find the optimal path at a given time, and maybe even adjust that based on what you have or what's available to you. Intent-based management, your network admin can indicate, okay, what I really want to have happen with my data traffic, my voice traffic, my video traffic, if you will, maybe limiting bandwidth for an application, etc. It can indicate that, and the WAN controller would institute some configuration changes needed for that to occur to make sure the voice and video gets priority, data gets second, or this type of data gets first priority, voice video second, and any other type of data gets third, kind of thing. Zero-touch provisioning. An SD-WAN edge device can be configured and shipped to a location or branch, and a non-technical employee or maybe one of your new IT techs can plug it in and get it going with minimal knowledge of that. So that can actually be done, your zero-touch provisioning. And some reduced costs, because I can use different types of WAN connections, maybe some less expensive ones, including DSL, cable, broadband, that sort of thing, for connections between. So overall, I might be able to reduce some costs of everything. Wireless WANs. Wireless WANs are specifically designed for high throughput, long distance. Remember our wireless LANs that we looked at back in Chapter 6? Your best 802.11 signal, you're talking maybe a few hundred meters. So anything beyond that, your wireless LAN technology is not going to cut it. That's where your wireless WAN technology comes into play. So your cellular networks, 4G, 5G, we're familiar with some of these. These can be initially designed for analog, but these can now be used for data and voice, which we know. We're familiar with that. So cellular, real quickly. First mobile phones became available in the 70s. Initially, it was just voice. It's now data and voice as well. Your coverage area is divided into cells, and those are basically created by putting a cell site at 3 different locations to create that cell. Cell providers will typically lease space on the tower for their antenna. So if you see a tower up there, there might be 2 or 3 different carriers up there with their antennas, if you will. Their antenna arrays, their panel arrays. So this tower might be owned by blah company, but you have 3 or 4 different cellular companies up here renting or leasing space on that tower. At the base station, your controller assigns mobile clients frequencies. Your cells are created by these towers. You have towers at basically 3 locations, and each one broadcasts out a lobe in like 2 directions to create this hexagon shape, this cell shape. Multiple cells share borders to form a network honeycomb pattern. Antennas are positioned at 3 corners, as we said. As a client moves from spot to spot or cell to cell, the towers do a handoff of like, okay, I'm going to hand this off to you now because the client's moving your direction. These base stations are connected back to a mobile switching center, which eventually connects into the central office. And here we're usually talking maybe a fiber optic connection going from the base station to the switching center. That's a lot of times what we run into. Cell size can vary, 1,000 feet to a couple miles, and it really depends on the topology and population. High population, they're going to be smaller. Higher population, these cells are going to be smaller. A smaller population to spread out, these cells might be rather large because they don't have as many devices in there connecting. And then here would be some mounted on the side of a building. Here's some concealed as a fake tree, if you will. And then, again, each base station is connected to your mobile switching office, also called MTSO. Each base station is connected by either wireless or fiber optic cable. A lot of times we're fiber optic. But if it's very remote, it might be a wireless signal. And that mobile switching center is going to do all of these: manage the mobile clients, monitor location, cellular use, assign each client an IP address, etc. If we look through the evolution real quickly, 1G was pretty much just analog phone in the 70s and 80s. 2G, we're talking the 90s now. We started getting digital transmission, able to do a little bit of text, a little bit of data, if you will. Just a little bit of text. I should say just a little bit of text. 3G, early 2000s. Now data rates have come up. We're either using GSM or CDMA. And now we're starting to get a little bit of, in addition to texting, a little bit of data. A little bit of being able to download data and get data. So 3G GSM, global system for mobile communications. This is popular worldwide. Using these types of technologies, time division, multiple access, time slots were allocated for users, and then several smartphones in an area were multiplexed together. So you might have seen that. You might have even remember running into or dealing with SIM cards, having a SIM card to basically be on that network. I remember changing SIM cards, moving from carrier to carrier. CDMA was another technology, GSM or CDMA. Here, you didn't necessarily need to worry about a SIM card, but they needed to be on basically a whitelist. This device is allowed on this network. Some did require SIM cards to use the LTE features. 4G, we're looking at, late 2000s, before we get to 2010, 2008, if you will. All IP network for voice and data. Now we're getting, the goal was to try to get to gig speeds, but you have the LTE and LTA variations. 4G LTE long-term evolution. This was faster than 3G, but not quite 4G. And your LTE-A was basically your true 4G. 5G, we're looking at late 2000s, late 2010s, early 2020. We'll get it out yet. And up to 20 gig down and 10 gig up with our data. So now we have a lot more data capability with our 5G. And some of us might actually be using 5G devices now. Many people are still using 4 because that's what you have and that's what works too. All right. That then brings us into some satellite internet service, satellite connection. Handful companies offer high bandwidth internet access via geo satellite links. They're typically asymmetric because you have your bandwidth shared by many subscribers. And this is the kind of thing you're dealing with. You have your uplink, downlink. Uplink to a satellite. Satellite sends a downlink to another site. This a lot of times is how, you have World Cup or Olympics that are happening halfway around the globe. This is a lot of times your connection to that event because of distance. 1960s was using satellites to transmit telephone and television. Today, satellite transmission can be used for voice, video, music, data, etc. Usually useful with your geostationary orbit of satellites. Satellites that are around 22,300 miles above the Earth. They are in a geostationary orbit. In other words, they are circling the globe essentially at the speed that the globe is turning. So that they stay at a stationary point above the Earth that can be used predictably for this type of connection. You can actually predictably hit it and receive data from it. So we have an uplink signal going to that's encoded. The transponder up there receives that, turns around, and sends it back down to a link on the Earth. This is all managed. Frequencies assigned and regulated by FCC for the U.S., if you will, but in the international, we're into the ITU-T for managing these sorts of things. And again, here reminding you, I put a little satellite uplink truck here. So if you go to like a live sporting event, they would have a satellite uplink truck hitting a satellite that's beaming down to maybe ESPN and or digital TV subscriber or direct TV subscribers and so forth, depending on who they're connecting to. These geosatellites are the key for allowing that to happen. But it is affected by weather. Satellite internet services, again, affected by weather, but for some areas that are very rural, this is a form of data connection. I just have a couple examples here reminding you of the types of services that you could be using from satellite. We'll come back in the next podcast and keep going.